Dr. Thaller.
Yes, like I told you, it's Michelle.
Michelle, thank you for joining us. Let's see. I wanted to introduce you, and so if you bear with me for a minute.
Why don't you have it?
It's 10 o'clock at night here. It's 10 o'clock at night. I get a glass of red wine.
I told Michelle we were going to be a very difficult audience, and that wine was very, very important. But anyways, Michelle is a Harvard-trained astrophysicist. She worked on her PhD, I believe, in colliding winds in close, massive binary systems, which I think is a study of Congress, isn't it? She is also
It's much more obscure than that, I think, yeah.
She's also the Assistant Director for Communications and Higher Education at NASA's Goddard Space Flight Center. She's appeared on the National Geographic Channel. She's an author and has appeared several times on the History Channel's Universe. And I know it's 10 o'clock back there, and so I want to get right to you. And everybody's anxious to not hear me, but to hear you as well. So I will run the animations as you direct me to do so. But we're very, very grateful that you're here with us, Michelle.
Well, sure. No, it would be very nice to be here. I'm really. We can keep this very casual. We can do whatever you like. I mean, I've prepared some animations. We don't have to show them all. We don't have to show them in order. I mean, it sort of depends on what questions people have. I mean, I'm happy to kind of launch into a few of them, but then if the conversation takes us somewhere else, that's fine. Yeah, this doesn't have to be a formal presentation. I believe I'm just about to accept the position as the Deputy Director of Science Communications at NASA, so I'll be going up to headquarters soon, I think. That's in downtown DC. But as George was saying, I'm an astrophysicist, but I'm actually, my actual title is Assistant Director of Science at Goddard Space Flight Center. And because that's true, I have to be able to keep tabs and represent all the different science that we do. And Goddard Space Flight Center has the largest Earth science department in the world. So, I'm actually, very much up to date as to what sort of studies are being done and what kind of data is coming out. And I'm happy to talk about that. George sort of wanted me to talk about the subject of ocean level rise, but as I mentioned, I'm happy to keep this very casual. So what would you like to do, George? Would you like me just to launch into a couple things, or?
I think that might be the best way to go. Of course, we're here on the Oregon Central Coast, and so sea level rise is something that is very interesting to us.
Yeah. I'm looking forward to being. I'm going to be in Oregon. I'll probably be somewhere on the Columbia River for the 2017 eclipse. So I'm looking forward to getting out there for that. But well, sure. If you want to pull up the first animation, we can just. I just sort of made notes as to what they were. This is actually just kind of a quick little bit of a one-off. I think it surprises people to know how much Earth science NASA does. And we actually right now are operating 20 different satellites that do nothing but study the Earth system. And I can't see what you guys are seeing, so hopefully George is having that running. But this always amazes me. I mean, Landsat's been operational for 44 years now. We have a 44-year record of what the entire land surface of the Earth is doing. And then we have things that measure the water cycle, sea level rise. We have satellites that can just measure the mass underneath them, and that this will turn out to be very interesting when it comes to sea level rise. So and this actually does not include things like the weather satellites, which actually NASA builds, but then gives to NOAA to operate. So these are 20 just research satellites all about the what's going on with the Earth. And the next animation, just kind of shows you some of the power of what you can do when you have all of these different satellites monitoring from space. This is actually a measurement of different sorts of air pollution. And the air pollution is color-coded. So the orange things that you see flying over the Atlantic, that's actually dust. Wherever you see orange and red, those are dust particles. That's a natural type of air pollution. The green that you see is burning carbon, either from burning forest fires or from actually rotting vegetation, lofting carbon up. And in fact, all the little dots you see down there, those are actually active fire sites. This is real satellite data. So we run all the data from these different satellites through supercomputers, and they allow us to see the world as a whole. no borders. The atmosphere all interacts with everything else. The white that you see, if you see areas with white smoke, that's basically from dirty coal burning. That's very sulfur-rich smoke. And we're learning all sorts of things about how the atmosphere acts. We're learning, for example, that over India, there's so much air pollution, it's actually impeding the monsoon clouds. The monsoon clouds are not able to get the convection they need to form properly. So there's a lot of climate effects, even just from the pollution that we put up there. So did you guys see that? I can't quite tell.
Yeah.
Okay, good. All right.
One thing I'm going to try to do, I think I can share my desktop. And
yeah.
I
If
wish,
you can't,
I
no
wish I
worries.
was an astrophysicist because that'll be a lot easier. But let me see if I can do that. So I've been showing the animations in a separate window. I think I can do that through Skype. So let me just see.
Like I said, no worries. I have little notes as to what they are. And so that kind of brings us to the question of sea level. We've been monitoring sea level rise from space for quite a while. We certainly have all kinds of people in the field, and we can talk about the people that we have on both the ice sheets and all the glaciers. NASA has many dozens of scientists that are flying aircraft over sea ice and land ice, are actually on the Greenland and Antarctic glaciers trying to measure what's going on. But, oh yeah, George?
Yep, I think I can do it. Let's see.
Oh, like I said, it doesn't matter to me. I'm happy to just talk to the ones luckily I made notes as to what these were all are of.
Yeah. So should I show number 3?
Sure. So this actually is a more satellite data, which shows you real measurements of sea level, obviously exaggerated. But I think one of the things that's sort of complicated about sea level rise. Oh, there you go. Yeah, I can see that. So this is from 2 of our satellites, Jason and Topex Poseidon, that actually measure the fluid height in different parts of the world. You can actually see there's a lot of variation there in the Arabian Gulf. But the ocean is not as flat as you'd think. You'd sort of be surprised to learn that there are actually sort of mountain ranges and valleys and big large-scale patterns in how high the ocean is, which depend on local temperature, on the way currents interact, on the salinity, the salt level of the ocean. So we can actually see these changes, but also sort of the natural large-scale patterns. And one of the reasons we haven't been so aware of sea level rise is because of the La Nina effect. There's a cold current off of California right now, and cold water is more compressed. It actually is lower and denser than warm water. So, right now there actually isn't a big ocean level rise. But one thing we're really going to watch is what happens with the El Nino this year. When we have warmer currents off the west coast of the United States, that might really change the ocean level. So just to tell you, ocean level is a complex thing. It can be very, very local. So one of the big challenges is trying to figure out where there'll be more ocean level rise than others. And that depends on things like currents, which are also going to change as the climate changes.
And one of the things that I was noticing in this as I was working with this video is the red is showing areas of ocean rise. And I think the white was showing areas of average or normal. And so it looks like in this as we look at this, you can see some particular areas where it's rising very, very.
That's right. Yep. But like I said, off the coast of the United States right now, we haven't been getting a lot of ocean level rise, but that may change. So it's not an easy thing. One of the frustrations of being an honest scientist is that people will say, well, how much is the ocean going to rise? And how much will the levels change? And we don't know that. We are trying to monitor. We're trying to model that also based on our computers. Yeah, George?
No, I don't know if anybody had any questions yet about what Michelle was talking about.
I do. I have read that the East Coast, the ocean is going to rise. The West Coast, it's going to go down. Am I reading the wrong things?
Well, it depends on which model, and it depends on what time. How many years in the future you're talking about. We are basically looking at global ocean level rise period. Everything's going to rise. The question is, how much? Some areas are going to rise much, much more than others. And there may be some localized areas where we don't get any ocean level rise at all, but they'll be very rare. So, we're at NASA, we're preparing for ocean level rise on pretty much every coastline. And let me give you a little sense as to why that's true. This is just sort of the fact that we can measure it from space. So, I'll tell you what, George, why don't you skip the next one for now and go to the one that ends with the numbers 4252? Yeah, we can come back to that other one. So yeah, give me the next one there. Right.
Okay, so,
So not that one, but the one under. Yeah. This actually shows you temperature anomalies going back nearly 100 years. So what you're looking at on the globe here is the yellow is areas where yellow and red are areas where the temperature is above normal for that area, above average, given any year. And then blue is areas where it's lower than average. And what you'll see is a really remarkable change starting in about the later half of the 20th century. And the real thing to watch is what goes on at the poles. So you can see that sort of holding there, that you can look at all of that red that's at the North Pole there. There's a number of things that are happening to really accelerate the warming of the planet by the poles. And there's such a delicate balance at the poles, and there's a lot of feedback. So when the air gets a little bit warmer, the ice begins to melt at the poles. And when the ice begins to melt, well, the ice actually acts like a big reflector on top of the Earth. It actually reflects sunlight back into space. So the less ice you have up there, the more the oceans absorb the heat. The exposed oceans absorb heat. That gets warmer, that melts more ice. So the poles have this real amplified effect when it comes to temperature change. And I mean, it's sometimes worth mentioning, depending on my audience, that global climate change is not any type of theory or conjecture. It's something that there's no academic disagreement about. So the entire argument that there's any disagreement among scientists that this is happening is actually not true. Certainly what is happening is a disagreement about how fast it's going to go, what the most significant contributors are, whether it's one thing or another, what will happen locally in different areas. So there's plenty of papers being published about the specifics and how we don't understand them yet and how we're working on our models. But the global temperature rise is absolutely confirmed. And we have substantial evidence that it's human-driven. It correlates almost exactly with human-driven carbon dioxide levels. So basically, if the Earth didn't warm in response to the carbon dioxide we're pumping out, that would be against the laws of physics. We model how much carbon dioxide is being released, and that changes the temperature of the atmosphere. So let me go down. Yeah, you can go down to the next animation, which I think is the sea ice. So as I mentioned before, the poles have these wonderful reflectors of ice, the ice caps. 90% of the Earth's fresh water, and there are two ice caps. And this is measurements of the extent of the Arctic sea ice over the last, 25 years, 35 years. It's been a long time. So the sea ice is decreasing very noticeably. And the more the sea ice melts, the more the oceans absorb heat. So that's sort of a feedback that we observe very deliberately. You'll sort of see here in the late 2000s when things really start to kind of tank for the sea ice. So this year we're on track to be the fourth smallest sea ice extent. It did go up a little bit again, but a lot of that is sort of local effects. The sea ice is also decreasing. It's something we measure. So this is something that I find, it's the next one I think is one of the most compelling sea ice rise contributors. We'll sort of go to these two. We have a satellite called GRACE, which is called the acronym stands for the Gravity Recovery and Climate Experiment. And there's two satellites that fly over the Earth continuously, about once every 90 minutes, and they do nothing but measure the mass underneath them. They can actually measure the amount of mass they're flying over. And they've been flying over Greenland every 90 minutes since 2004. And this is the mass of the Greenland ice shelf, being the land-based ice on Greenland. And the amazing thing to me is that the ice shelf on Greenland has been losing close to 200 billion tons a year. The scale that you see over on your right-hand side, the scale on the bottom, it says gigatons. That means billions of tons. So in the last, since 2004, in the last 10 years, Greenland has lost 2,500 gigatons, 2,500 billion tons that has not been replaced to the ice cap. And that is water going into the oceans. That's water that was on an ice shelf that is now going into the oceans. That effect is now so well along that there's really no way to stop it. I mean, we don't know how much of the ice sheet of Greenland is going to melt, whether it will all melt eventually or just a little bit will melt. But even right now, things are out of balance. We've already started things melting, and there's nothing we can do to stop that, right? I mean, there already is latent heat in the ice that needs to melt out for centuries. So, we have bought ourselves a couple of centuries of climate change, even if we sort of cap things off the way they are right now. And Antarctica is a little bit scary in it's the same way. If you go to the next animation, it's the same type of measurement, but this time for Antarctica. And Antarctica was actually largely stable as of about 5 to 7 years ago. And from 2004, you'll kind of see this pattern, especially what we call the Western Antarctic ice sheets, which means they're close to South America, they're close to the Western Hemisphere. You'll notice there's sort of a red color where we're losing ice, and you'll see the graph keep going down. But after being relatively stable, the Antarctic ice sheet is beginning to lose, again, on the order of between 100 and 200 billion tons a year. And it's lost 1,500 gigatons in the last 10 years. And, these two ice sheets combined, I mean, just the ice sheets that are melting right now are going to buy us at least a couple of feet of ocean level rise, over the next 100 years or so. And then, it's not likely to happen anytime soon, but if the ice caps, if Greenland completely melts, that's more like a 30-foot rise. So, that's not something that would happen fast, but that is something that if we keep the atmosphere out of balance, could eventually happen in some centuries. So, one of the websites that I go to that I actually think, I don't think everything that NASA does is brilliant, but there's a website called climate.nasa.gov. And you can go in and you can see all of the measurements about sea ice, about carbon dioxide levels, about ocean level rise. And you can just see for yourself the data that we're taking. And, this is something that it's sort of kind of a comfort for me, even if it's a little bit of a cop-out. At NASA, it is our duty simply to provide the data. We are not a political organization. We serve whatever administration, the people elect. And so, we do not advocate for any specific policy. I can't tell you, what policy we should do to solve this. I can't really advocate anything like that. But what I can do, and I feel very empowered in this, is share this data with everybody on the planet. This is completely free, completely non-copyrighted. We are constantly going to places like the United Nations or the IPCC or other governments all around the world to show them what we're measuring. So, sea level is definitely going to change. I don't know exactly where in the Oregon coast will be most affected or exactly how fast it will go, but it's not going to be business as usual, in the next 50 to 100 years. We will see very dramatic changes. So let's see, there's a couple other things I could show you. So actually, if you go to the next one, this is kind of a funny one for us on the East Coast. A little bit unfortunate, but we were talking about global temperature anomalies and how it's, things are getting warmer on average. But you'll notice this was last year's averages over the United States. And you can see that it was just basically the eastern half of the United States was like the only place on the planet besides well above the Arctic there that was actually colder than normal. And we really have this dichotomy in the United States now because of the jet stream. The jet stream is beginning to wobble and vary much more than it used to. And it's pulling down, they're calling it a polar vortex, pulling down cold air over the eastern United States, and it's pulling up warm air over the western United States. So I think you guys had a very warm winter last year. And we unfortunately are due for another cold one, I think. The thing that's happening, this is actually a prediction of climate change. If you go to the next animation, we have a number of scientists that are trying to model what happens as the poles warm to the jet stream. And the jet stream is this river of wind, these sort of high velocity winds that it's sort of locked into place by the temperature difference between the pole and the equator. And when that temperature variation lessens, when there's actually less of a temperature variation, you can see what happens is you get these huge variations in the jet stream. And that's one of the reasons why we're telling people that, unfortunately, climate change means hotter temperatures locally and colder temperatures locally. It means extremes get more extreme. And one thing that seems to be happening is that we're actually seeing fundamental changes in the jet stream. And because of the lack of temperature difference now between the pole and the more temperate regions. We have several aircraft missions that fly up to the Arctic and try to measure the energy balance of the clouds and how all this is working. So, we really are trying to figure out what's going on there. and also apply computer models to it as well. And the next one, if you want to go to that, I mean, so we have an extremely powerful computer at Goddard Space Flight Center, and we are running models. And as I said, these are computer models. We don't know these are true or not, but we're trying to figure out what happens if we don't stop the amount of carbon dioxide increase in the atmosphere. And if for some reason that has trouble running, don't worry about it. It wasn't a major one. But we are trying to model where we're going to have extreme droughts. And like I said, don't worry if that one doesn't run. But we actually see some interesting predictions that if we can manage to cap carbon dioxide about where it is now, we only have about a 50% chance of having what we're terming mega droughts, meaning droughts that last for more than 30 years. So even the Dust Bowl, in the 1930s, that was about a 10-year drought. So we're talking here 30-year droughts. If we continue to go, if the carbon dioxide continues to go up in a manner that it is today and on that same line, then you've basically bought yourself an 80 to 90% chance of 30-year droughts in the latter half of the century. So we're trying to figure out what all this does to the Earth's climate. And while we don't have all the answers yet, the answers are not good if we don't do anything. And so one of the things that we're trying to make sure people understand, we're now. We have been for quite a while. I think the problem is there's never a single cutoff, but we're in the phase where we can choose different futures. There are futures that are climate change is going to happen, but it's something we can deal with more or less, and there's ones where it's much more difficult to deal with. So we really just I think there's every chance that we can make some kind of a treaty, something that actually regulates our carbon use. Like I said, I can't advocate for anything specifically. One little bit of optimism I'll leave you with, and I actually, hold to this a lot. At Goddard Space Flight Center, we were actually where the ozone hole was detected back in the 1980s, where they realized there was actually a hole in the ozone layer of the Earth opening up near Antarctica. And that was due to chlorofluorocarbons, chemicals that we were using for coolants that were actually breaking down the ozone layer. And this was detected by a NASA satellite. And NASA scientists and many others from universities around the world went and lobbied the United Nations, and there was a treaty called the Montreal Protocol that banned most of these dangerous chemicals. And we now have evidence that the ozone hole is actually healing, that the ozone is actually coming back in these areas where it used to be depleted. And we've run our lovely supercomputer to show how long would it have been until the ozone layer would have been mostly destroyed if we'd done nothing, if we had not worried about the chlorofluorocarbons. And our model suggests the ozone layer would have been mainly depleted by the year 2060. That's only 45 years from now. And we've exposed crops to the amount of UV light that we think would be getting through the atmosphere at that point, and they almost all die. We would have seen the collapse of agriculture and, probably not able to have livestock outside. People couldn't live outside very much. That would have been extremely bad in 45 years. So we actually averted a horrible thing because we got together and we wrote a treaty and we realized we had to do something about it. And if anybody says you can't do anything about it, right, that it's all gone and you should just sort of, be depressed and all die, we're now able to choose at least less bad futures as opposed to, really bad futures. And, I actually gain a lot of hope from the fact that at NASA, we helped advocate for things like the ozone layer healing. And whenever anybody says that, federal science isn't worth anything, what's NASA done for me lately? I'm always like, grandchildren, you want grandchildren to be alive in 45 years? Yeah, that's your tax money at work, yeah. Okay, that's a little bit of an introduction about some of the work that's being done. I know I also included a video of some of our scientists flying over the poles, trying to measure the extent of the ice and see what's going on, how fast it's going. We can show that or not. I'm happy to answer questions too.
That might be good. Sure. I think, yes.
I have confusion about carbon footprint in that it's continually said coal is bad, electricity is good, but 70% of our electricity comes from coal. 20% comes from nuclear, which isn't much more of a warm fuzzy for me. I don't see a solution here. If you get rid of coal, you get rid of if you get rid of fossil fuels, I mean, apart from solar, which is only, I think 4%. Well, and I know those are United States statistics. I don't know world statistics, but what direction should we be going?
Well, as I mentioned before, as a civil servant, I can't advocate any specific policy. Right? So, yeah. So one of the things I can say is that solar does have a relatively low carbon footprint, right? So, solar energy, you're not releasing any carbon into the atmosphere. I think you need to be very careful about this. I think that you've hit upon something very important, and that is that people will tell you something is green or something is energy efficient, and sometimes you really need to look at that. I mean, if you're going to be building, massive solar windmills and it takes you a lot of transportation costs to get the materials there, you're flying giant turbines on planes or you're bringing them by trucks, you need to be very careful about how much carbon is actually being used. So, I mean, I would say that, I'm very optimistic about some of the very high efficiency solar panels that are coming online. At NASA, so, I mean, we had to invent solar panels that work out by Jupiter, which is so far away from the sun. The sun is basically kind of a bright star in the sky. And, we have incredibly high efficient solar panels and batteries. I think that does offer some hope for, less carbon usage over time. But yeah, that's the whole idea. We have to stop putting carbon into the atmosphere. And yes, that does link to fossil fuels. We have to stop using fossil fuels, I think. Yeah.
There was another question.
Here on the West Coast, we're really hearing a lot about this new El Nino, and that it's an unprecedentedly large El Nino forming very early in the season. Mm-hmm. The blob, have you heard about the blob, the general warm water off the Pacific coast here, Central Coast?
Yeah.
I'm wondering, is this part of the heat sink where the ocean is getting capacitated with radiation or just warm air or whatever? I mean, can you comment a little bit about this coming El Nino?
Not much. So this is what I told George. When George asked me, I said, I'm an astrophysicist, right? So, I'm not an oceanographer. I do certainly have friends who are. But, I think you've heard what I've heard. I mean, I've read the releases that this is an extremely large El Nino. I don't think we know exactly how it's going to manifest yet. But this is where, I will be absolutely honest to you what I do not know. And I can't tell you much more detail about that. I'm sorry.
We'll get a couple more questions because I know it's very, very late. Usually when I hear the blob, I always think of the governor of New Jersey. But that. There's another question.
So the relationship with the warmer temperatures to the bigger storms, the more violent tornadoes and big so you have the insight on.
It's a prediction, right? I mean, it's something that, kind of makes sense. I know that, we've been studying hurricanes a lot, and we have a number of different ways at NASA of doing that. I mean, we've got all the satellite. We've just launched a satellite called GPM, the Global Precipitation Measurement Satellite, which actually has this dual frequency radar that cuts through the hurricanes. You can actually see layer by layer where all the energy and the precipitation is. And then we also have aircraft that we fly with people on them. And then we actually have drones. We actually have Global Hawks, drone aircraft that we fly through hurricanes. So, we have a very dedicated campaign to study whether the intensity of hurricanes is increasing. I believe some preliminary data suggests that it is, but there again, I'm going to go back to the fact that George asked me to come, but I'm not an oceanographer. So it's a prediction of climate change that you will see more intense storms. Yes.
Just a question that came to mind: are the forecast models? Do they give NASA the capability of understanding, like, if China wants to build 5 more coal plants? Does it give NASA the ability to plug that information in and look at the model and how that impacts, the trending information? I mean, is it down to that component level that if these are coal plants as opposed to nuclear plants or solar wind, this is how we believe it will change the outcome?
Well, it all comes down to the amount of carbon you release into the atmosphere. And coal plants release a lot more carbon than, nuclear plants or solar power or what have you. So, I don't think that we have models that say this many coal plants buys you this much, temperature rise. But we do have ones that say this much more carbon dioxide will buy you this sort of a path up in climate. So, like I said, it's that, I want to be very careful. I can't necessarily advocate against the coal industry, right? So, what we can tell you is how much carbon you release and what that will buy you in terms of a temperature change. But I don't know anybody who's actually broken that down into how many coal plants that is.
And, there's lots of yes.
Based on your knowledge that you have, that you understand, could you give us an idea, where are we going to be, say, 20 years from now?
Well, you can actually go into nasa.gov, the climate.nasa.gov website, and you can see these trends. So you can actually look at the trending data for yourself. And, one of the things that's the most worrisome for us is we don't understand what the slope of those trends is going to turn out to be. For example, when we look at the mass of Greenland and Antarctica, it's not necessarily a linear relationship where the ice is just going linearly down. The rate of decrease is increasing, right? I mean, the amount of ice melting, that's getting faster. Yes. And we don't know where that's going to end. Yeah. So, this is one of the big questions is does that level out? Or do we actually just see the ice decrease faster than we expected? So, as I mentioned before, I can't give you answers about what's going to happen, in what schedule. That's something we're working on. Certainly, we're going to see, a couple feet of ocean level rise in the next century. I think that's pretty much guaranteed. The question is it somewhere around 2 feet, or is it somewhere around 5 feet? And that has tremendously different repercussions for how we will be able to adjust. And that's something we're talking about, within the next 100 years.
Mm-hmm. Yeah. Another question, and then one more in the back.
I just wonder, what do these satellites measure in terms of temperatures? Is it just the surface, or how deep does it go, for instance, in the ocean?
Yeah, the satellite measurements, I think, can basically just give you a surface temperature reading. We do have lots of buoys, and we actually have people in situ, in the ocean, actually measuring deeper ocean temperatures. And that's another really interesting area of research, is how is the deep ocean responding now to is it actually changing temperature at all? Is it very stable? One of the things that we're kind of worried about is there's a massive current that actually links all of the Earth's oceans. It's called the thermohaline conveyor. And the word thermohaline, thermo means heat, and haline means salt. And this huge current is actually just driven by differences in temperature and salt in the oceans. So up by Greenland, actually, Greenland has all this fresh water coming off it. It's very cold. So the current gets very fresh water, very low salt, and very cold, and that actually drives the current to go all the way down to the bottom of the ocean. And the Greenland area is actually where oxygen connects to that current and gets carried to the bottom of the ocean. So it's incredibly important. It delivers oxygen to the deepest parts of the Earth's oceans. And one of the problems is that as Greenland is melting so fast, and as it's changing the chemistry of that water, what will happen to that current? Will we actually see that current shift or change somehow? And so, we're actually looking to see what happens in the deep oceans, based on the changes in temperature and salinity. So, satellites, I think, will mainly just give you surface readings. That in itself, as far as temperature and also height, the height of the water will also give you a sense about how much things are expanding under the increasing temperature. But the deep ocean, I think you need somehow to get there and take the measurements at that depth.
And I think there was one more question.
Yes, you mentioned the solar panels that NASA has working on Jupiter. And I was wondering if that level of technology is available and accessible for application for.
Yes, we have an entire office at NASA that has no other purpose than to get our technology out to spin-off companies, get it out to use. And so, we very much, I can't tell you exactly how many solar panels we could produce of that quality, but I do know that's something we have, really, really good people at NASA, hundreds of them across the agency, working on getting that spin-off technology out as fast as we can. Yeah.
And one more?
Yeah, what do we know about the link between climate change and population?
Well, it's not going to be good for population, I think. I mean, climate change is going to disrupt, where people live, the crops they can grow. I know that there have been some estimates about how many refugees we will have to deal with, come about, again, around about the 2060 timeframe, in about 40 years. And some people are placing them in the hundreds of millions of people that are displaced by climate change, either because there's a huge drought and they can't grow their crops, or literally the ocean has taken over their coastline, or many other things. So, I do think that one of the things we're going to have to look at is how to deal with large-scale refugee crises on the planet.
We should have ended on the optimistic note.
It's not easy, it really isn't. I mean, we talk to children about this. I'm always sort of figuring out how to phrase this, how to couch this. It's not a lot of good news, but we are also, I think, as a species, very resilient, and there is a challenge coming up now. I mean, I think it's going to be the Apollo program for the next generation is going to be how do we deal with the changes climate change is going to bring, and it doesn't necessarily have to be apocalyptic. But it's going to take some large-scale organization, because when I think of, hundreds of millions of people being refugees, there's never been that large of a human migration before. And in history, that tends to rewrite borders. So, I think that, if we get together, I mean, they're having the climate conference in Paris coming up. NASA will be there with all of this data and more. And not just that, but, we understand people don't respond to graphs and just to data. We want to make sure we're bringing the emotional connection, the personal story about why we need to figure this out as a planet.
You see some of it with other countries. Like I understand some countries in Europe, in terms of the question about energy portfolio, have really shifted to a majority solar and wind portfolio, which I would imagine would greatly reduce in terms of operations and on the carbon footprint in those particular countries.
Yeah, we've noticed there's an air quality improvement over China. I mean, we can monitor air quality all around the world, and there are areas of the world where they seem to be getting a little bit more serious about cleaning things up, about being more cognizant about what's being released into the atmosphere. So, I mean, I think it'd be a great shame if the United States was not a leader in this. I think not only is it letting history pass us by, but even on something of a selfish level, if we have the best solar panels, if we have the best new technology for this stuff, we should be out there trying to figure out how to develop a big industry to get this stuff out around the world, make it a global product. And I think that we could be leaders. I hope soon we stop arguing over the fact that it's happening and that it's human caused, and we get down to the real business of trying to figure out how to deal with it.
Let's hear it from Michelle. Late night with us.
That's right. Time for bed. Okay, well, you guys have a nice evening. And I did tell George, by the way, that I wasn't an oceanographer. I said, hey, do you want an oceanographer? He's like, oh, no, we want you to come and talk to us. So if you have specific questions, George has my email, and I can try to find people who will tell you, about what's going on with the hurricanes, what they're measuring, or about the blob, of warm water. Those people are all my friends. I know which building they live in, so I can find them.
Wonderful. Thank you so much again, Michelle.
Thank you. You guys have a good day.